Take a look at section 3.8. I have the recording running, guys. Okay. 3.8. Here it is. I'm just going to start with a question, let you kind of get a taste of what we're getting into here. Okay, and these just take practice, and they're kind of our patterns. I mean, every book does the same kind of questions, it seems like, and this is always one of them. Talks here, it says, water runs into a conical tank at the rate of 9 cubic feet per minute. That's a volume. The tank stands point down and has a height of 10 feet and a base radius of 5 feet. How fast is the water level rising when the water is 6 feet deep? Okay, this is the kind of stuff we're getting into in this section. And when you see questions like this, they tend to feel a little bit overwhelming. You just kind of have to jump in there and just give it the best shot. You have a cone with water going into the cone. Okay, that's what your cone looks like. And there's water going into the cone. Water is running into this conical tank at a rate of 9 cubic feet per minute. This 9 cubic feet per minute is dV dt. That is the volume, the increase in the volume as water is entering the tank is 9 cubic feet per minute. That's the change in volume, the increase in volume in the water in the tank. The tank stands point down and the height of the tank is 10 feet. So from here to here, this is a 10-foot tank. And the base radius is 5 feet. So this radius from here to here is 5 feet. How fast is the water level rising? So you have water in this tank, and as water is going in, the water level is increasing. So the water level is rising. Let me read this again. How fast is the water level rising when the water is 6 feet deep? Okay, so the water level, the height of the water here, I'm going to just use X and Y. So I'm going to let this be Y, being the way the water is, that Y is changing, the height of the water is changing as the water is entering the tank. This radius of the water in the tank is also changing. Those are two things that changes as the water level increases in the tank. So we can let that be X. Now, you got to think of a formula to start with, something to do, evidently, with the volume of a cone. Does anybody remember the volume of a cone? Try. What'd you say? Pi r squared, height times the area of the base. Okay, so it's 1/3 the volume of a cylinder, and a cylinder is pi r squared h, so it's 1/3 pi r squared h. The pi r squared is the area of a circle, which would be the top of the cylinder, and the height is the height of a cylinder, and it's 1/3 of it. So it's 1/3 pi r squared h. Well, we're trying to play, or I'm going to try to stay with x's and y's. And so if I stay with x's and y's, this will be 1/3 pi instead of r squared. This will be x squared instead of h. This will be y. Okay, so now let's read the question again. Water runs into a conical tank at a volume of 9 cubic feet per minute, which is your volume. The tank stands point down and has a height of 10 feet and a base radius. How fast is the water level rising? Okay, how fast is the water level rising? If y is our water height, then the fast would be dy dt. The change in the height of the water is dy dt. Okay, so what we have is we have volume information and we have height of the water information. We don't have anything on x. We have too many variables here and we don't have any information on x. So we need to figure out how to get rid of x. We want everything in v and y, and x needs to go. So the goal is to eliminate x. Well, then it won't be varying anymore because it's full. You're running off. Okay, so this is very typical of pretty much every question you'll ever see when it comes to a cone being filled with sand. The other one is you have sand dropping into a pile, which is a cone, the opposite direction. So this is the way it always works. Look at the picture. You have a proportion in this picture. X is to y as 5 is to 10. Okay, so x is to y as 5 is to 10. So 10x equals 5y, or x equals y halves. So to get rid of x, replace x with y halves. So this becomes v equaling 1/3 pi y halves squared times y. So finally you have v equaling what? Y halves squared is y squared over 4, right? So this is 1/3 pi times y squared over 4 times y. So this can be rewritten as pi 12ths y cubed. So now you have two variables that they gave me information about. So now what I'm going to do is take the derivative. They told me that dv dt is 9, so when I take the derivative, I'm going to get dv dt, which can later be substituted with the value of 9. So now let's take the derivative, which is giving the changing stuff, the water level moving, everything kind of in motion. So this becomes dv dt equaling pi 12ths is a constant, so you're really just going to take the derivative of y cubed, which means you pull a 3 out front of the pi 12ths. You decrease the 3 by 1, and implicit differentiation has taught us that you now have to write this as dy dt. Because everything is changing with respect to t, so it's kind of like implicit differentiation using t, changing with respect to time. So there is your equation that you're hoping to kind of work with a little bit. Let's see what we know. We know dv dt is 9. Do we know what y is? And when we freeze time, this is what I call when we freeze motion. Freeze time. Take a picture. This thing is moving constantly, but we're going to freeze it. And we're going to freeze it when water is at 6 feet deep, right? We're going to freeze the picture at 6 feet where y is 6, so we do have y. So we have everything here except dy dt, which is the question. You understand what's going on here? This was the question. We have this value. Yep, we're good here. The y is 6. We're good here, and the only thing left is dy dt. So dv dt is 9. Y is frozen at 6 feet high, is when we're stopping the process at 6 feet high, kind of taking a snapshot of everything in motion. And now just clean this up. So that could have been a 4th. So this is what? 36 times 3. I don't do this well. 36 to 3. Is that 9 pi? Yeah, that's 9 pi dy dt. Divide both sides by 9 pi, and you get 1 over pi equaling dy dt, which I've already done this before class, which is approximately 0.32 feet per minute. So the height of the water, y, which is our height of the water is changing at 0.32 feet per minute. So you know how long to let the water drip before it overflows, kind of thing. It's telling you how quickly the height of the water is moving as you're putting water in at 9 cubic feet per minute. Okay, I'm getting kind of some unusual stares, people still writing very quickly. All right, let's try another one. Number 2. Yes, I sure can put it back up for you. I tried to wait until I thought everyone was through writing. This, well, 1 over pi is 0.32, approximately. 1 divided by 3.1416, approximately. 0.32 feet per minute is the change in the height of the water in the cone. You ready now? Okay. Okay, here's another question. Hot air balloon. They always do hot air balloons. Okay. A hot air balloon is rising straight up. And they kind of sort of go straight up, right? Okay. Rising straight up from a level field, and it is tracked by a rangefinder, which I don't know about rangefinders, but there's some rangefinder out there, 500 feet from the liftoff point. At the moment the rangefinder's elevation angle is pi force, the angle is increasing at the rate of 0.14 radians per minute. So how fast is the balloon rising at that moment? Okay, so really what you do is you kind of draw a picture and you try to see if you can pull a formula out of your head to work with the information given to you. So you have a balloon. Okay, got a balloon going on, some basket underneath it. And a hot air balloon is rising straight up from a level field, la 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 la. It doesn't say anything about how high this thing is off the ground. Okay, it's off the ground, but it came straight up. Somewhere out here is some device called a rangefinder, and it is 500 feet away from where the balloon lifted straight up off the ground. At the moment that the rangefinder's angle is pi force. Okay, so they freeze time. Okay, everything is in motion. You got some device here whose angle is moving up as it's clocking this balloon, but they're going to freeze it whenever this angle right here, this thing's shooting some laser or whatever, when this angle here is pi force. So when it's frozen at pi force, the angle is increasing. So the change in the angle increase, is 0.14 radians per minute. So they just gave me d theta dt, which is the rate at which the angle is increasing. How fast is the balloon rising? So everything's in motion, but we're going to freeze it at whatever point that theta from this rangefinder is at pi force. So when they freeze it, it says how fast is the balloon rising. So if our vertical is y, the question is, what is dy dt? How fast is the balloon rising? Now, we got to look at all this stuff and figure out how to come up with some formula. Note that you have theta, you're looking for a vertical value, and you have a horizontal value. So what trig function would best apply? There you go, tangent. We know that tangent of theta is going to equal the y over the 500, right? There you go, or y equals 500 tan theta. We're looking for dy dt, so that's good. We got some theta stuff going on. Okay, we can do this. We need to take the derivative. Okay, so now everything's in motion. So you want to take the derivative first. So you have a formula while motion is taking place, and all this is moving. We're just kind of cheating time by freezing it at some point. So we're going to take the derivative, dy dt, and it's going to equal the derivative of tan theta secant squared theta. So this is secant squared theta d theta dt. Think of implicit differentiation. Okay, so we have a formula. Now let's look at what was given. Do we have enough information to answer the question? The question is, what is dy dt at that moment that we froze time? We know that d theta dt at the moment we froze time was 0.14, which fills this one. Theta at that frozen moment in time is pi force, so we're good. We got everything we need. So here we go. dy dt, let's substitute values, is 500 secant squared theta. Secant is 1 over cosine, right? So I'm going to put 1 over cosine of pi force squared, and d theta dt was 0.14. Now you got to pick pi force. You can't put 45 degrees there because 0.14 is in radians also. Okay, so what is cosine of pi force? Square root of 2 over 2. So this is 1 over square root of 2 over 2 squared. So what is this? This is 1 over 2 fourths. What does 1 over 2 fourths equal? 2. One thousand times 0.14 is 140. So with this cool little angle finder thing, track range finder thing, okay, it's telling us that if we could have stopped time, which we really can't. Yes. Mm-hmm.
What is the starting one from the bottom in the brackets? What's that bottom?
Square root of 2 over 2. Square root of 2 over 2. If we could have just stopped time, you see a whole lot of, film options where you freeze time, kind of funny now. If you could have been there watching the balloon go up, knowing that that rangefinder thing is over there on the ground somewhere, if you could have just frozen everything in position at that instant, that balloon was rising at 140 feet per minute. Okay. So before you substitute known values in, you have to have the derivative. Before you substitute, you must have the derivative because things are in motion and you're freezing time, so you only substitute into your equation, which is going to be the derivative. Right? Are we ready to turn the page? Okay, I still see somebody writing quite very quickly. Yes, I have definitely worked these before class to make certain I can explain them to you. Okay. All right, let's take a look at the next one. A police cruiser approaching a right-angled intersection from the north side is chasing a speeding car that has already turned the corner and is now moving straight east. When the cruiser is 0.6 miles north of the intersection and the car is 0.8 miles to the east, the police determines with radar that the distance between them and the car is increasing at 20 miles per hour, and you know he can do that. But he shouldn't be doing that while he's driving the car, right? Okay, whatever. So if the cruiser is moving at 60 miles per hour, and you know he's braking because he's coming to the intersection, he's got a lot going on, he's shooting that gun, he's coming to it, probably a busy intersection, okay? This would not pass safety standards, okay? If the cruiser is moving at 60 miles per hour at the instant of measurement, what is the speed of the car? Okay. He surely has a seatbelt on, right? Okay. Okay. So here we go. Whoa, let's tear that up. Okay. So here is the policeman, and he's headed toward this intersection going terribly fast. Okay? And he's got this gun sticking out the window kind of thing, right? Here goes the car this direction. So here's the policeman going south. Let me read it. Police cruiser, la, 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 is chasing a speeding car that has already turned the corner. When the cruiser is 0.6 miles north of the intersection. So let's let this be Y. When you freeze time, when all this is in motion, okay, that last minute picture before he wrecks his cop car kind of thing, okay, when he's 0.6 miles from the intersection and the car is 0.8 miles, and this is horizontal, so let that be X, the car is 0.8 miles from the intersection, the police determines when he's shooting that gun out the window across a field. Try to visualize this. This is like a field. When he shoots that radar over, he's hitting this car. And when he hits that radar toward that car, he notices that the distance between him and the car is increasing at 20 miles per hour. Okay, so what would be 20 miles per hour? How would you label 20 miles per hour?
Well, that would be change in the hypotenuse.
There you go. The change in the distance between the police car and the car he's chasing is this distance. So the change in that distance, dz dt, its change is 20 miles per hour. The distance between them and the car is increasing. At 20 miles per hour. Okay. All right. So here we go. This one's not too bad. Now, let's think about this. What do we know about, is this a right triangle?
Yep.
What do we know about right triangles? How about x squared plus y squared equals z squared? Okay. Okay. Do we have information about x, y, and z? Yes. So we don't want to eliminate. Well, you got dz dt, so you can't get rid of z. Okay. So you have all variables. You don't want to get rid of any of them because you have information about all of them. So you're going to take the derivative of this equation, and you need every one of these variables because you have information about all of them. Okay. T, time. Everything's with respect to time. So 2x dx dt plus 2y dy dt equals 2z dz dt. Oh, get back up there. Okay, what do we know some more stuff? Oh, the cruiser is moving at 60 miles per hour. What's that value? dy dt. Now, this is where it gets a little confusing. But is his dy dt is like his velocity, right? Is this decreasing or increasing? Decreasing because he's slowing. No, he's not. He's going to be flying through that intersection. Right? He better be on the brakes because he's coming to the intersection. So this is negative because he's slowing down. And he's going south, and he's going down. He's going down. He's going in a south direction. He's going in a down direction, which is a negative direction. Okay. That's right. The distance from the intersection is getting smaller. Very good on all that. Okay, so what do we have? We have x. We don't have dx dt, which is probably what we're looking for. What are we looking for? What is the speed of the car? That's what we're looking for, right? Okay, dx dt is what we're looking for. Do we have y? Yes, it's 0.6. When we freeze time, we can substitute stuff in here because this is our motion equation, so we're kind of stopping things in motion so we can put them into this formula. Do we have dy dt? Yes. Do we have z? No. Can we find z? Yeah, because when we freeze time, we have all these angles. We have, not angles, all these distances. So to find the length of z, we use, Pythagorean's theorem. Make certain everything is on. Yeah, I thought I heard something click. Okay, so, I don't know, real quickly, I'm going to put this on here. If this is 0.8 and this is 0.6, what is this going to be?
1.
Wow, thank you. So 0.6 squared plus 0.8 squared is going to be z squared, and they said that was 1, so z is 1. So now we have all the values. So this is 2 times 0.8. dx dt is what we're looking for. This is 2 times 0.6, and dy dt is negative 60. This is 2 times 1, and dz dt, and that's increasing, is 20. So all we have to do is clean this up, and we have dx dt, which is the speed of the car. So this is what? 1.6. Ooh. What is this? Is that right? Okay, so we got 1.6 dx dt equaling 40 plus 72, which is what? 112? Divide both sides by 1.6. What'd you get? 70. There it is. That's how fast that car that he's chasing is heading eastbound. He's probably picking up speed. You know, he's just gunning it, right? Okay, so this is the speed of the car. Okay. All right. And again, this is negative. This is where I have the biggest difficulty, is knowing when these things are negative. This is negative because his distance is decreasing as he gets close to the origin or the intersection. Okay? All right, this one. I don't like this one. I don't Well, for some of this one, I really don't like this one. That's okay. Okay. Y'all might love it. A particle P moves clockwise at a constant rate along a circle of radius 10, centered at the origin. The particle's initial position is 0, 10 on the y-axis, and its final destination is the point 10, 0 on the x-axis. Once the particle is in motion, the tangent line at P intersects the x-axis at a point Q. Okay, so what this looks like, okay, you got a circle with radius 10. Something like that. Okay. Particle P moves clockwise at a constant rate along a set of radius. The particle initial position will. Once the particle is in motion, the tangent line at P intersects the x-axis at point Q. Okay, let me see if I got a straight edge somewhere around here. Okay. The tangent line at point P intersects the x-axis at point Q. All right, there we go. The tangent line at point P is intersecting the x-axis at point Q, which moves over time. Okay, Q is going to move because if your tangent line is here, that's where Q is. But as your tangent line moves, right, Q is going to move. Right, it's getting closer and closer. So Q is moving in as the particle is moving along the circle. All right, it takes the particle 30 seconds to travel from the start to the finish. It's starting up here and it's ending here. How fast is the point Q moving along the x-axis when it is 20 feet from the center of the circle? Okay, what in the world do we know? Okay. From here, let's think about all this, okay? Okay, can you agree that this radius is always 10, right? And that this theta right here is going to definitely be changing. So we got a theta amount that's changing. We know that R is constant. It's not changing because it's stuck at 10. They want to know about Q, and this Q movement is on the horizontal axis. So this is our X. Okay, the Q's movement is playing with X. And so dx dt is interesting. In fact, is that what they're asking? How fast is point Q moving? Okay, dx dt is the question. How fast is point Q moving? Okay, and now let's talk a minute about d theta dt. Let's think about this. Do we know d theta dt? I think we kind of could figure this one out. Okay, it says, where did it say something? The particle, right, it takes the particle 30 seconds to travel from start to finish. So it takes the particle 30 seconds to move this quarter of a circle, right? So in other words, it changed pi halves radians, right? Radians in 30 seconds. And I took this from the book and they didn't want to use seconds. It must have made the numbers bad. So 30 seconds is 0.5 minutes. And I'm not certain why they changed it, but they definitely did it this way. I don't know. It makes the numbers work out. Because pi halves divided by a half is pi, right? Which is pi radians per minute. So d theta dt is pi radians per minute. Now this is where it gets interesting. Is this a right triangle? Yes, it is.
Right there, that point.
Why is it a right angle?
Because that's a normal line.
Isn't the tangent going to always be a right angle to the circle? Oh, yes. Okay. Right? The normal is going to cut right into it, right? But the tangent's always going to be perpendicular to that. Okay, so let's kind of get try to get this vision. Here is the triangle. Here's the right angle. Here's point P and here's point Q. And here's theta. We're dealing with x. We know this side is 10. So which trig ratio would best apply to this situation? Is it not that cosine theta would be 10 over x? Right? Cosine theta would be 10 over x. Y'all see that? I'd have to spin it. Oh, wow. Would cosine theta equal 10 over x? Yes. See it? Okay. Spin it back. Don't look. That'll make you sick. Okay. So cosine theta equals 10 over x. Or x cosine theta equals 10. Or x equals 10 over cosine theta, which is the same thing as secant theta. 10 needs to be in front. 10 secant theta. So now that we're there, we've got to get dx dt. So we've got to have x because we're looking for dx dt. Okay, and we know what d theta dt is. So we're looking for x and theta to be in this formula, and there it is. So now let's take the derivative. So dx dt equals 10. What in the world is the derivative of secant? It is. Is it secant theta tan theta? Yeah. Secant theta tan theta. The derivative of secant theta is secant theta tan theta, and then don't forget d theta dt. Okay, we're looking for dx dt. What in the world is theta? Do we know d theta dt? Yeah. We just need to know theta, right? Okay, now if we freeze time, because we're stopping motion and we're really freezing time, it said that when you freeze time, that's when d theta dt is pi radians per minute, and that's when q is 20 feet from the center of the circle or 20 feet from the origin, right? So when you freeze time, this x is 20. Okay. So now let's see if we can figure out these trig ratios, right? Okay, dx dt equals 10. What is secant theta? Well, I got to change it myself. Secant theta is 1 over cosine theta, right? I have to change it for me to be able to do that and do that well. Okay, so this is 1 over, what is cosine theta? 10 over 20, adjacent over hypotenuse, 10 over 20, which is a half. So this is 1 over a half. Tangent theta is opposite over adjacent. Oh, crud. That's opposite over there, right? There's no number sitting there. But by Pythagorean's theorem, what in the world is going to be the length of this side? There you go. You got Pythagorean's 10 squared, but whatever this thing is, maybe we'll call it, I hate to call it y, we'll call it b. Okay? So b squared equals 400 minus 100. So b would equal the square root of 300, which would be 10 square root of 3. So this is 10 square root of 3. Okay, so tangent theta, there you go, it's 10 square root of 3 over 10, which is going to be square root of 3. And d theta dt is pi. These 10s are going to go. So, and this is going to become a 2. So this is 10 times 2 times the square root of 3 times pi. So this is 20 square root of 3 pi. What? What's the unit here? This is how quickly Q is moving toward the origin. Feet per, we changed everything to minutes, okay? So if it was radian per minute, this will be feet per minute. That's how quickly Q is moving. And it should be negative, right? We need to make it negative because the distance is decreasing.
That's for speed. Yeah, speed bonus. Speed's absolutely
How fast? How fast? I don't know if they want speed. I don't know. They didn't say the word speed. Yeah. When you do your homework in this section, if it's because of the negative that's throwing you off, just be certain you write all your homework down. I can probably override the grade. Okay. Number 5. A jet airliner is flying at a constant altitude of 12,000 feet above sea level as it approaches a Pacific island. The aircraft, we have time, right? Yeah. Okay. The aircraft comes within the direct line of sight of a radar station located on the island, and the radar indicates the initial angle between sea level and its line of sight to the aircraft, like that other little device that was on the ground by the hot air balloon, okay? And it's 30 degrees. How fast in miles per hour is the aircraft approaching the island when the first detected by the radar instrument if the radar is turned upward at the rate of 2/3 degrees per second in order to keep the aircraft within its line of sight? Okay, so we have a plane up here in the air, way up there. Okay, we got this instrument over here on this island. He's up here at 12,000 feet. You have some kind of a little instrument over here that is shooting an angle up to that plane. Okay. So this is like theta. Okay. How fast is the aircraft approaching the island? So we want to know how fast is this plane going, which in the horizontal direction is dx dt. That's the question. How fast is the plane approaching the island? If we freeze time, because it's first detected by the radar instrument if the radar is turned upward at a rate of 2/3 degrees per second. Okay, so what is d theta dt? I know, 2/3 degrees per second. They did that kind of a mess, okay? In order to keep the aircraft within its line of sight. I don't like this 2/3 degrees per second thing. Okay, we're going to have to convert that. Let me see if I can figure out why we have to convert it. I can tell you why we have to convert it. What did it say up here in the question? Aircraft comes to this, First of all, that plane, okay, is 12,000 feet. Here's the problem. That's in miles per hour. And this is in seconds. Oh my. Okay, and 12,000 is in feet. Everything is in the wrong. Okay, and I'm trying to think. The answer to this thing was written in miles per minute. Okay, so they should have said, and I think that in my math lab you'll see it next to the answer blank. We want the answer in miles per minute. Okay, the answer is in miles per minute, so everything has to change. So 12,000 feet needs to be converted to miles. How many feet do we have in 1 mile? 5,280 feet per mile. So that gives me miles height in mile units. This is degrees per second, and I need minutes. So this is 2/3 degrees in 1 second. And there are 60 seconds in 1 minute. So this gives me what? 40 degrees per minute, is that right? So this equals 40 degrees per minute. Well, we don't like to work in degrees, believe me. You don't want to multiply by a degree, you want to multiply by a radian. So we have 180 degrees in pi radians. So this ends up equaling 4 over 18, which is 2/9, right? Pi. Let me make certain we're on track here because that's not what I have in my notes. That would be radians per minute. Okay, so this is 2 pi 9ths radians per minute. Okay. And this figure, did I get this figure ever calculated anywhere? 2.27? All right. So we have an angle, we have a horizontal, and we have a vertical. So what's the trig function? This is kind of like dx dt here too, guys. The plane's not on the ground, it's in the air, but... So, yeah, so I didn't leave a whole lot of room on this page, did I? Let's see if I can kind of fit in here. Okay, how about tangent of theta equals 12,000. 12,000 is not changing, right? Equals 12, oh, I did. Equals, I like 12,000 better, 2.27 over x, or x tangent of theta equals 2.27, or x equals 2.27 cotangent of theta. And there's our formula. Okay, let's take the derivative. Oh, the derivative. Okay, the derivative now will be dx, I hope I have enough room, dt equals 2.27, and the derivative of cotangent is negative cosecant squared. So this would be times a negative cosecant squared theta d theta dt, and we do have d theta dt. Okay, so now dx dt is what we're looking for. D theta dt is given to be 2 pi rads per minute, 2 pi over 9th rads per minute. This is, I better put this in parentheses. This is not looking good. Okay, I better put that in parentheses. And cosecant theta is 1 over sine theta. And what is theta? Did they tell us that? Yeah, at 30 degrees. Okay. So we got the d theta dt. It's the theta here that's a little bit concerning. But up here it says when you freeze time, the line of sight will be at 30 degrees. Let's get out of degrees though. So freezing time at pi 6. So we have it all. So here we go. dx dt equals 2.27. I don't like cosecant. So I'm going to put the negative in front. So this is 1 over, cosecant is sine. So sine of pi 6, and after you get that, you're going to square it. And d theta dt is 2 pi over 9 radians per minute. So dx dt is a negative 2.27. Okay, sine of pi 6 is sine of, I have to go back to 30 degrees, and that is equal to No, that's 45 degrees. So if this is 30, this would be 1, 2, square root of 3. So sine of pi 6 is 1/2. So this is 1 over 1/2 squared times 2 pi over 9. This is radians, don't forget, per minute. So what does that equal? That's a negative 2.27 times 4 times 2 pi over 9. So what does that equal? No, that's not right. What did you get again? Negative point what? Maybe that is right. 0.52? Miles per minute. Yeah, it's got to be a little more than that. Don't forget the pi. Maybe it was negative 0.252 pi. Did you come up with a different number? Negative 2.27 times 4 times 2 times pi.
Yeah, which is negative 57, then divided by 9 is negative 6.3.
Negative what? 6.3. Miles per minute. And why is it negative? There you go. The distance is closing in. Decreasing distance to the camera or the island. Decreasing distance is why it is negative. Okay. What time do we leave? Okay, good. We're okay. Starting to panic. I'm thinking, what time is it? How much time do we have? I feel like we're running kind of slow. That's okay. Okay, one more. All right, what is this one? This is straight from the textbook. Oh, come back. Come back. Okay, and they give this diagram in the textbook. What did I put on there on page 160? And we'll sketch it too. But they have, come back, come back, come back. 160. A diagram. Here's a picture, and I'll pretty much replicate it on this paper so you can kind of see where M and P and W and everything are. All right, so here it is. This figure shows a rope running through a pulley at point P and bearing a weight W at one end. So you have a pulley. You got this weight hanging down from this pulley. Okay, pulley at point P and the weight on one end. The other end is held 5 feet above the ground in the hand M of a worker. So over here is point M, and it's 5 feet above the ground. Suppose the pulley is 25 feet above the ground. All right, so if I can get this here. Okay, hold on here. I'm going to put the origin at the guy's hand, okay? So if this is the ground right here, this is 5 feet, and this distance from here to the ground is 25 feet. Because the man's 5 feet tall or whatever, to the hand or whatever. Suppose the pulley is 25 feet above the ground. The rope is 45 feet long, and the worker is walking rapidly away from the line PW, and the weight's supposed to be W, from the line PW at a rate of 6 feet per second. I think the weight was W, maybe the origin was W. This guy is moving this direction. We're going to call it dx dt at a rate of 6 feet per second. Let's hope all the units are the same here. Feet and feet. Okay, we're good. How fast is the weight being raised? Okay. How fast is this weight going up? We'll call that dy dt. Okay. The question is dy dt. How fast is the weight going up when the worker's hand is 21 feet away from PW? Let me look at this again. well, 21 feet away from the origin. They keep saying W, but it's coming from the origin. Okay, so here we go. We got this rope that's 45 feet long. This is bound to have something to do with Pythagorean's theorem. If the guy is 5 feet tall, or his hand is 5 feet above the ground holding on to this rope, what is the distance the pulley is from the ground? That's 20. Okay? This is what we don't know right here. So this is what we're going to let be a distance. And I'm going to stick to my notes. So let me find my notes. We're going to let that be y. All right. And let this, do I need that one? No. Okay. So here we go. I like to use x, y, and z. So dx dt, here's y, and let's let this be z. We have this 45-foot rope, all right? So this 45-foot rope is the length z plus this length here, right? The rope is going from the man's hand to the weight. So if this is y, oh, how am I going to fit it in here? This is 20 minus y, right? So the length of the rope is z plus 20 minus y. All right. Okay. Now let's take a look at a triangle that we can apply Pythagorean's theorem to. This side is 20, this side is z, and this side, when you freeze time, we're going to know this side, right? Okay, so we're going to end up using Pythagorean's theorem to make this happen. So we also know that x squared plus, I don't want to use y, plus 20 squared equals z squared. And this is kind of where we want to work, is with this one. Okay, we have an x and a z, and we know nothing about z. We got some information here about y, and we want to know dy dt, right? So we need to get rid of z, and we need to get y. Okay, we need to get rid of z. And we like y. We got to get y, because y, we're looking for dy dt. So how are we going to do this? Okay, let's take this 45 equaling z plus 20 minus y, and let's solve it for z. To solve it for z, if I subtract 20 from each side, I get 25 equaling z minus y, or z equals 25 plus y. So this equation becomes x squared plus 20 squared equaling 25 plus y squared, and finally we have an equation in x and y. Finally, we have an equation in x and y. And that's what we want, because we're talking about dx dt and dy dt. So we need an equation in x and y. And we know nothing about z or dz dt, so we need to get rid of the z. Okay, so we're going to have to take the derivative of this thing. Let's change that to a 400. Okay, let's take the derivative. Okay, so we're going to have 2x dx dt plus the derivative of 400 is 0. I shouldn't have put that there. Okay, and then over here we're going to use the train rule. 2 times 25 plus y to the first power, and then the chain rule says take the derivative of that polynomial, and the derivative of y is 1 dy dt. So we get 2x dx dt equaling equaling, I'm going to distribute the 2, 50 plus 2y dy dt. Okay, what do we know? Do we know enough? Okay, 2, we're asking for, we got dx dt. We know that, do we know x? Because we're taking the derivative with respect to time. T. Okay, we do know x. How fast is the weight being raised when the worker's hand is 21 feet away? And it says PW, but from the origin, so we do know x. X is 21. X is 21. dx dt is 6 feet per second. Y, we don't know what y is. Can we come up with y? I came up with y. How did we come up with y? Oh, we can come up with y. How are we going to get y? Okay, stop thinking geometry and just look at all the equations on your piece of paper.
C plus 20 minus y equals 45.
Well, we don't know anything about z. Look for an equation. You know x. So look for an equation that only has x and y in it. How about this one right here? We know x because x is 21, right? So if x equals 21, what must y be? There you go. You have x squared plus 400 equaling 25 plus y squared. Because that's the thing we're missing. We're missing that y. So here we go. So x is 21, so we get 21 squared plus 400 equaling this 25. I don't want to, let's don't do anything with that 25 plus y. Leave it alone. 21 squared is something big. Okay, so this is 441 plus 400. So this is 841. Okay, now if I don't want to distribute, what do I do now? See if 841 is a perfect square. Very good. We just, they wrote this question just for us. Okay, so y is 4. So now we're ready to go. Now we can fill this formula in. So now we're good. So now we have, so I make a loop. Look at my lines everywhere. We got here and realized we need some more information. We go up there and grab it, get the information, and we come back. This is the process, okay? Circle around and come back. Okay, so here we go. So here we go. This is 2 times 21. dx dt is 6. This is 50 plus 2 times 4. And dy dt is what we're looking for. So this is 2 times 21 is 42, and 42 times 6 is... No, 42 times 6 got to be a 2. Is it 252? Okay, and this is 50 plus 8, which is 58. So divide both sides by 58, you're going to probably get a decimal. Okay, 4.34 somethings. What is that? Feet per minute, feet per second, feet per second. This is, now look at your diagram, if you can find the diagram up here. dy dt is how fast vertically the weight is moving up toward the pulley. So you're moving upward. The weight, when this guy is, what did it say, rapidly walking with the pulley to the right, must not be a whole lot of weight for him to pull it quite that easily, then this weight is lifting at a rate of 4.3 feet per second. Rising Okay, that's what's going on. Now, these are not necessarily what I consider fun. Okay, and y'all got really quiet right with me. So go in there, and I tried to pick homework examples that run along the same line as these that we did in class. Go in there and see what you can make happen, okay? I didn't pick like extremely hard questions for the test because I know this is kind of difficult, but you do need to get in here and try to get comfortable with these, okay? They're not going to go away, all right? We do have a test next week. Make certain you come in ready for the test. I think the quiz was really pumping you up for it. I feel good about your algebraic skills. It's just getting through this 3.8. So get your homework done, and I'll see you on test day next Monday.